I'm Rachel Gehlhar, and I'm a rising fifth-year PhD student at Caltech. Today, I'm excited to talk to you about my ongoing research on a powered prosthetic leg. On the right is a picture of me with the prosthetic. It has a motor to control the knee and a motor to control the ankle. It's designed for someone with an amputation above the knee. It also has this adapter so that I can strap it to my leg and do testing with it, even though I'm not an amputee. In the lab I work in, we focus on making robots walk like people. You can see an example of this humanoid walking in our lab. I specifically focus on translating the math we use to control walking robots to a powered prosthesis. In this presentation, I'm going to use the word controller a lot, and that basically means a mathematical function, we call it U of X, that determines the torque to apply at each joint. So it's the math that decides what to tell the motors to do so that the robot behaves as we want. To motivate why we're studying powered prostheses in general, I'm going to talk about the limitations of currently available prosthetic devices. Here's an example of a commercially available prosthetic device that has a knee joint and an ankle joint. And here's a video of a man walking with this prosthesis. It looks like he's walking all right, but this device is limited because it is not self-powered. It does not move on its own, and so amputees end up expending around 33% more energy in walking than able-bodied walking. Powered prostheses, on the other hand, are self-powered. They move on their own, such that the user expends less energy in walking. Also, we can use them to assist with more challenging behaviors like stair climbing. And further, we can develop controllers to keep the human safe. Today, I'm going to talk about 4 research projects that I've had the opportunity to work on in my time as a PhD student. I'm going to start with 2 projects that are in line with my main research path. My first project goes back to the idea of translating math from walking robots to prostheses. The reason we can't use the math directly from a walking robot to a prosthesis is because on a walking robot, we have sensors on every joint, and this tells us what the whole robot is doing. They act like eyes. But for the prosthesis, we don't know the human's behavior. So the prosthesis is essentially acting blind to what's happening above it. For my first project, I theoretically proved that we can use a force sensor and an inertial measurement unit, or IMU, to control the prosthesis with the same methods as walking robots. So this force sensor measures the interaction forces between the human and the prosthetic. And this IMU sensor measures the rotation of the human's thigh. And this gives us enough information about what the human's doing so we can apply these same control methods we use for walking robots. This is really significant because now we can control the prosthesis with 2 sensors as well as if we knew what the whole human was doing. In this video on the left, the prosthesis is being controlled with knowledge from these 2 sensors, knowledge of the force and the rotation of the thigh. And on the right, the prosthesis is being controlled with knowledge of what every joint of the human is doing. And the behaviors are identical. So now we can take these advanced control methods we have for walking robots and put them on the prosthesis. However, one problem that comes up when we think about putting this on hardware is that force sensors are really noisy, meaning the measurements we get from them, those numbers jump around a lot. And so this can really mess up our math. For this reason, we developed a method to estimate this human interaction force without a force sensor, but instead using motion capture. For motion capture, we have these reflective markers on me and the prosthesis. Then I walk around in a room with cameras that track the motion of those reflective markers. A computer records this motion of the markers, and then we can play back that motion in our human prosthesis simulation. When we play back this motion in simulation, we can calculate that interaction force. And so we do this for multiple steps, and then we obtain a whole range of what those interaction forces are that the prosthesis sees from me. With this range of interaction forces, we can now control the prosthesis to keep the human safe for any force within this range. Now I will talk about 2 collaborative side projects I've gotten to work on. The first was in Telluride, Colorado last year for a 3-week workshop. Here I met Chang, and he developed a recurrent neural network to learn our controller function U of X instead of computing it exactly. Now, what is a neural network? It's a type of machine learning that can learn how to behave like a function without knowing its actual mathematical expression. So in our case, our inputs are what we know the prosthetic is doing. And then U of X is our mathematical equation that calculates how much torque to send to each joint based on what the prosthetic's doing. And so the torques are outputs. Now the neural net takes place of this mathematical equation. And it learns with data how to go from what the prosthetic is doing to the desired torques that we want. We ran this neural network on a small processor that fit on the prosthetic. Now this is really special because while machine learning is a growing field, it's very difficult to get machine learning to work on hardware, especially hardware that's small enough to fit on a prosthetic and fast enough so that our prosthetic can respond very quickly. Here is a video of our results. On the top, I am walking with a regular controller, and on the bottom, I am walking with the neural network controller. These motions are indistinguishable, and as I was walking, I could not tell a difference between the two controllers. This means that the neural network learned our control method very well. But what's the advantage of having a neural network if it just replicates our previous controller? Why would we want to use this? Well, although in this case, it just replicated it, it gives us now a tool to use for other current problems we're facing with the prosthesis, because having machine learning that works on the prosthesis is really special. So one of these current problems is these advanced controllers I've been talking about that we have for walking robots. To put them on the prosthetic, it requires a lot of coding because of all the math. And this takes a while to compute, which could slow the robot down. But instead, we could have a neural network that could act just like that controller, but with less coding, and it could compute it more quickly so that our robot could respond very fast. The fourth project I worked on was with another group at Caltech that developed an electronic skin sensor that sticks to human skin and is powered entirely by human sweat, meaning it doesn't require a battery. This sensor goes across the elbow and detects when the elbow bends. So we put this sensor on me to then tell the prosthesis when to take one step. So when my arm was straight, the prosthetic knew to hold still. Then when I bent my elbow, the prosthetic knew to take one step forward. Here's a video showing this in action. So you can see that when I bend my right elbow, the prosthetic takes one step forward. You may also notice that this video is running at 3 times the speed because this current state of research for this sensor, the sensor is running a bit slowly, and so I had to walk in slow motion to take this video, which is why we sped it up. So although the sensor isn't at a state where we can keep using it with the prosthetic, it provides this proof of concept that we could use it as a human-machine interface so that the human has more direct control over the prosthesis. Previously, to make the prosthetic start walking, I had to lean into it and push it forward so it knew I wanted to take one step. But with sensors like this that could detect my motion, it would be much smoother then for the prosthetic to recognize when I want to move. This concludes the work I've done so far in my PhD. And my next goal is to implement these controllers that I had working in simulation onto the physical prosthesis. Most of my work so far has been in simulation and theory, which I can do mostly on the computer. And about mid-March is when I finished up those projects and then wanted to move on to putting these controllers on the prosthetic in lab. And you may also remember that that is when COVID hit and the stay-at-home orders went in place. Thankfully, I got to take my robots home with me. And so I'm working on setting up a small lab environment at home so I can continue working with the prosthetic and try out these new controllers on it. With that, I would like to acknowledge my advisor, Dr. Erin Ames, as well as the co-authors on the papers of the projects I mentioned today, Jenna Rare, Michelle Chen, Cheng Gao, and Yu Yu. And if any of you would like to get in contact with me or have questions about my research, I'd be happy to answer any questions. Here is my email address. Thank you for your time and attention today.